Gauss's law, the subject of chapter 27, is not universally covered. We're not going to be covering it for credit in this class. Why not? Because the mathematics of this chapter, the calculus of this chapter, where we're integrating over surfaces, that is it's something that you've done, but it's one step beyond, at least one step beyond the other math that we're doing. And chasing down that additional level of calculus will take time away from other things that I really want to make sure that we cover. However, I'm going to take a little bit of time to talk about that material. I'm going to require you to watch this material because there are some concepts we'll need to know. And when we get into looking at magnetic fields, magnetic fluxes, this material will be important. And when we tie this all together into one set of equations, Gauss's law is one of those equations. Now, we have electric charge. For this point, I'm going to start off with our most simple version, the electric field of a single point charge. Now, let me draw the field lines going out. And in fact, let me draw a lot of field lines for, hopefully, clarity's sake, going through. Now, again, there exists no, this charge means this many field lines, but we do have to keep things proportional. If I have another charge that has half the charge of this first point right here, I should draw that, for consistency's sake, with half the number of field lines. And the field measures, try and make that more of a straight line. Well, at any given point, the field lines tell me the direction of the electric field. And, if I'm breaking this down, there should be a way to mark down the strength of the electric field at that point. There's one other concept that we haven't really talked about. Consider that if I have this surface, like so. Now, if I move that surface, changing nothing else, trying desperately to keep this at equal length. Now, this surface, this green disk that represents, let's say this represents a circular surface. Now, what's different about these two places? Well, first off, to talk about the electric field at any given point, then it'd be hard to begin with, because the electric field at any point will be different, because each place will be a different distance away from the point charge. But even in the more central cases, we can see that there is some difference, some different interaction within the electric field, depending on where this surface is. Heck, let's look at it like this. If we look at this point, I've got 5 electric field lines passing through the surface at its closest approach. But when I move the electric field, that surface a little bit farther away, I've only got 3 electric field lines. Now, I'm going to define a quantity which we're going to call the electric flux. And flux think of flux as like well, flux comes from the root word, the same root word that flow does. So it has to do with the number of field lines. So let us say it is proportional to the number of field lines passing through that point. Now, I can't just say, oh, well, in that case here, the electric flux, and I'll use a capital letter, Greek letter phi, for the flux. Well, I can't just say, oh, hey, here, flux is 5, and here, flux is 3. Well, I cannot say that because the number of field lines is utterly arbitrary. I could have drawn this, so this had 10 field lines, and this would have been like, 6 or 7. Or some different number. So, but I can look at that and I can say, okay, that electric flux, it's got something to do with the number of electric field lines passing through it. So it's got something to do with the electric field and the area. If I were to come through here and take, say, this little section and zoom in on it, I would have some differential area dA, and that area would have a differential vector dA, and the direction of this vector would be normal or perpendicular to the surface. That would have, looking at the electric field at that point, the electric flux would be proportional to the electric field and the area of that differential piece of area, but the flux will be the highest if the electric field and the area, if those two vectors are parallel. The electric flux will be the lowest, 0, if those two vectors are at right angles to each other, because then I'd have, if I have the electric field at right angles to that little tiny differential piece of area, dA, then that means there is no electric field going through the surface, it's all going along the surface. So at this point, the flux would be 0. So, I'm going to define the electric flux as the electric field, the electric field dotted with, taking the dot product with the differential area vector, and this will give us a scalar, which is cool. We're looking for a scalar electric flux. We're just trying to measure the electric field flowing through that surface. So if I integrate that over an area, hey, I've got the electric flux. Now, what I'm going to do is I'm going to look at this in 3 sneaky bits right here. And the first thing that I'm going to do, put my definition of the electric flux equal to the integral of E dot dA. And again, if you haven't done a lot of vector integration, don't be too alarmed, because what we're about to do is we're going to sneakily avoid a lot of the problems inherent in this integral. I'm going to take 3 special cases and try and do an end run around some of the complexity.